Good evening. I am Daniil Kovalchuk. The topic of my report is analysis and computer simulation algorithm of radar imaging by continuous wave linear frequency modulated synthetic aperture radar. Sorry, have some problems here. So antenna aperture radar systems, or SAR, hold a unique position among remote sensing technology due to their ability to produce high-resolution images on Earth's surface better than 1 meter resolution, and most of all, independently of natural illumination and weather conditions. These formulas represent the mathematical description of signals. First is sensing signal with linear frequency modulation, transmitted form. Received is similar to transmitted. The only difference is time delayed by delta t. So time it takes to obtain the target and get back. And final step involves multiplication of 2Z signals, which needed to extract phase difference between two signals and gut information value. Based on literature analysis and derived equations, these four approaches, along with the various modifications of temporal or spectral processing, we've gotten in SAR, used in SAR, LFM SAR. First is temporal processing in both horizontal range and azimuth. So the black diagram for omega k algorithm that were used as example is here. Next is spectral processing and horizontal range and temporal processing in azimuth with modified omega k algorithm. Next, spectral processing in both. Temporal processing in horizontal range and spectral in azimuth is the third one, and the last one, both spectral processing in azimuth and horizontal range. These algorithms, which form radar images from received raw data, represent the primary methods used in linear frequency modulated synthetic aperture radar. Let us now explore the methods used for simulation modeling of these existing algorithms. So, according to the theory of optimal signal processing in radio systems, the resolution is defined by its impulse response function, which characterize the system's response to a point source of radiation. And following this approach, the developers of algorithm presented in simulation modeling often use a test image consisting of a single bright point on a dark background. As depicted on figure point matrix, evenly arranged in a square area in the ground seen with distance, both interval azimuth and range. Simulated linear frequency modulated continuous wave synthetic aperture radar data on an array or just a single point target. But the radar images represent the surface reflection coefficient and is typically displayed in grayscale, with black indicating zero reflection and white indicating full reflection. As you can see at slide, surface roughness and dielectric constant of a targeted surface are dominant factors in determining the amount of radar backscattering. Then, previous approach fails to determine the potential accuracy and performance limits of the system. To develop exact optimal algorithms, the problem must be correctly formulated based on established measurement principles. Adequate radar image modeling of underlying surfaces is needed to obtain the quality of these methods. For instance, narrowing the main lobe of the antenna pattern does not always enhance the quality of the radar image. A more effective approach is to slightly widen the main lobe and reduce the side lobe levels using the weighting windows, which help suppress interference from objects with low reflectivity that are otherwise would be masked. Therefore, a more appropriate methodology for certifying radar image formation algorithm in LFM-SAR should include models of radio signal reflection by underlying surfaces that close resemble to real conditions. We will examine this methodology using a sensible signal in SAR with processing of continuous LFM signals. That block diagram shows us that method. For simulation, the true radar image and its evaluation. This algorithm repeats all mathematical calculations that would be used here, but in view of the model, we can say that random process in the form of wide spatial noise with power spectral density that is within the limits of the other function of integral to integral. Because of the amount of that, here we have a model of sensor LFM signal with some characteristics 100 megahertz as here and 30 milliseconds duration here. So next slide shows us the noise components that we added to the radar image and the components real and imaginary. Which act as an amplitude multipliers in the received signals by two channels of raw data processing. And here we could see selecting the geometry of sensing form of the UA that have taken the range farthest to 3,000 meters with speed 50 meters per second and radio wavelengths as 3 centimeters. So the raw data which lead us to radio hologram before processing on first figure here. The received signals are being processed using the algorithms described on previous section. Here we could use omega k algorithm. So here's results and enlarge sections with needed to show exactly multiplicative noise which arises due to the random reflection of electromagnetic waves from real surfaces and their coherent processing in LFM synthetic aperture radar. And the last one shows us the size of speckle noises, which corresponds us to the width of the system's impulse response function. As conclusion, the algorithmic steps for generating test radar images were detailed, including an example of their implementation by using exactly MATLAB software. Unlike existing methods, the generated radar images contained multiplicative speckle noise, which closely resemble real examples. That's it. Thank you for attention.
Yeah, we are done with this part, the question part. If not, we will go to the risk assessment.
Okay, thank you again.
Thanks. Yeah.